Hello students, Gilly here. This week, you probably know there's no new theory, but we're going to focus on R. So I'm recording a series of videos where, in essence, we're going to revisit many of the things we've discussed in the theory part of the unit, but now applying them in R and trying to do a few things that we're not able to do with pen and paper. Now, this video is the first one. It's going to be relatively basic things. I just want to show you how to plot different probability functions. Maybe you've done that before. I'll try to point out a few things that are maybe new to you, but okay, this video should not be too complicated. So I just want to be able to plot the density, the mass function, and the CDF of any given distribution. And then also we're going to simulate random variables or sample coming from a distribution. Then we want to plot its histogram, okay? And also its empirical CDF. But first things first, now let's assume we have a distribution. So a theoretical distribution, let's have as an example for a discrete distribution de Poisson. Here, just declaring arbitrarily the lambda parameter to be 1. So I just want to plot the mass function at every integer value. So arbitrarily, I'm going to choose the range of those integers to be from 0 to here. Ceiling is taking, I believe, the rounded up value of whatever is here, and here arbitrarily I'm going as far as 5 standard deviations from the mean. Okay, so I'm taking the mean, which is lambda plus 5 times the square root of lambda, which is also the standard deviation. Okay, and then I use function plot, which I'm sure you've encountered before. It's simple syntax. The first argument is all our x values, and then the second argument needs to be of the same length because it's associating with every x a y value, so a value on the y-axis. And here use a d Poisson. D Poisson is the I guess d for density, but here it's a mass. But so the mass at every x. So you see, I'm passing inside d Poisson the series of values for Poisson, and that's about it. Everything else is graphic parameters, okay, to make our graph a bit neater. So let me just send this to R. Okay, let me make this a bit bigger. So you see, we have our mass. So it shows the probability to be 0 is 30-something%, to be 1 is 30-something%, and then it decreases. Of course, if I had picked a lambda difference, say 5, you would have gotten something with a very different shape. Maybe just a second on all those things. This is just the size of those bars. Well, type, I'm asking for bars here, because I think if I put L for lines, it's going to be something pretty ugly, I think. Oh no, it's not ugly. It's just, it assumes it just wants it's a continuous line, but that's probably not what we want in this case, because those are masses. Okay, and so on. Here, color, you can pick your favorite color. I really like brown tree, but maybe you can find which is your favorite R color. I'm naming the axis both y and x and y. Okay, here main is for the title, but you see it's a bit of a weird syntax. B quote just allows you to put some mathematical notation. So here I never remember this by memory, so I always need to Google it, but I'm not going to spend too much time on this. But in essence, with B quote, I can put a sentence, but then those symbols, I think this creates just a space, and then it's mathematical notation. So R knows that lambda should be the actual symbol. You see the actual symbol here, lambda, in the title, okay, and not the word lambdas. And then equal would be just equal, and then that's interesting. Dot lambda, dot whatever is going to be recognized to be the R object, which is called lambda. So you see, this lambda here is the symbol, but dot lambda is the actual value in the R session. So you see, this is why in the title you have lambda, the symbol equals 5. Now, all of that, again, is not massively important, but just for your information, if you want to have nice titles to your plots. Okay, and those are changing the size of the size of the title and then the size of the labels. But again, not super important. Okay, I guess it's not the main point. Let's do the same thing for the CDF. So here I'm going to start a CDF at -1 just to see, to make sure it's 0 for negative values. So let's see. And again, I'm going to just plot. Now I'm using P because P and R is the name for obtaining the CDF of any distribution. Well, any distribution that's implemented. Okay, and then let me try it. Okay, this is what I wanted to show you. Here, type L is probably not what I want because it's a, again, it's discrete distribution, so it has jumps. I probably want to see the jumps. Okay, so if I type S is for step, I believe, and it's going to actually show you the jump. Okay, so let's try. Yes, much better. Okay, much better. You see the jumps. Okay, if I go back to lambda of 1, I'm going to see the jump. Now it's not perfect because ideally I'd like to see here to be empty, because in reality it's a jump, right? So at 0 the function is equal to 0, and then at 0 point, sorry, I'm sorry, at any negative number the function is 0, and then at exactly 0 the function jumps. Okay, so here probably you would prefer not to see this sort of bar. I'm sure there's a way to do it, but we're not going to get into that. Okay, maybe later, and probably maybe ggplot would be better capable of handling this. But anyway, you have it, the CDF of a Poisson. And of course, I leave you maybe as a exercise. You can adapt those to have a different distribution. You can try this for negative binomial, and so on. Yeah, here of course you would need 2 parameters. Okay, let's see a continuous case. Kind of arbitrarily, I picked the gamma. Gamma has 2 parameters. Now I'm going to fix the mean of my gamma to be 2, and then I'm going to change the shape. So let's just start again arbitrarily with a shape of 2, and then if I want a mean of 2, I want the rate parameter. So that's the second parameter in the formula sheet. It's called lambda. Okay, shape would be the first parameter alpha, and then rate would be lambda. If I want a mean of 2, I'm gonna take the shape divided by the mean, and that gives me the rate. And then here, okay, I want to show you. So here we've used plot, but now I want to show you how to use curve. And I would say, I think in general, I prefer to use curve when we're plotting something that is a nice smooth function, like a continuous function, such as a density. Okay, the density, of a continuous random variable, or the CDF of a continuous random variable. So how curve works is that instead of putting X a series of point and then Y a series of point, you actually give it the actual function, and then you give it a range of where to evaluate it. So let's have a look. D gamma is the density of a gamma in R. So here, this is the first argument is always X, so don't touch that. Okay, and X, careful, it means the arguments of this function D gamma. It doesn't mean a series of points like it was here. Okay, and then I give it, so I give it a shape equal to shape. Okay, that may be slightly confusing. Let me explain. Shape here, the first one is the name of the argument of the D gamma function, but I can equate this to whatever shape means in my specific R session. Okay, so I'm basically here I'm passing to the argument called shape the value 2. Okay, because shape in my R section is equal to 2. Okay, if you find this confusing, maybe you would prefer to avoid those things, you can call this shape 1, and then say rate 1, and then here shape equals shape 1, and then rate equals rate 1. Okay, if you want to avoid the sort of rate equals rate. But anyway, now what I was saying, this is the first argument of curve, but then I'm telling it explicitly where to plot this function. Okay, plot it from 0 to a bound, and again, a bound is something I've declared here, just arbitrarily. Here I'm taking the mean plus 3 times the standard deviation. Okay, you could have put 4 if you wanted, or whatever. Okay, and then that's pretty much the interesting things to say. So let's try it. Okay, of course, shape not found. Where do I need shape? But I thought I had declared shape. Yeah, of course, here. If I change the name of shape to be shape 1, I need to change it. Okay. This is real-time updating of the code. Okay, the shape is somewhere else. Of course, it's here. That's okay. I should learn not to improvise. Okay, then third time is a charm. Let's go. Okay, so we get our nice density for the gamma. Now let's just do it again with a different so a shape of a shape of 4. Now I still want my mean to be 2, so I'm going to take rate to be shape 2 divided by mean again. Okay, and you see, with curve, I could create a new plot, but let's say I want to add this new curve for the different gamma on the same plot. I can have this argument add equals true, and I'm going to add the new curve for the new gamma on the same plot. Okay, now you see, you don't see the top because it doesn't adapt the range. Okay, it's just gonna pick the range of this one. Now, to fix this, because I do want to see the top of this other density, there's an argument in curve and also in plot, which is x lim and y lim, but here it's y lim, basically telling R explicitly what's the range in which it should plot those functions. Okay, so here, okay, it should start at 0, which is already what it's doing, but then I want it to be higher than 0. Whatever. Okay, let's try 0.5 to see if I can see the top of the green curve. Let's try again. Yes, I do see everything now. Okay, because I've manually changed the top here. Maybe I could have put yeah, I think 0.5 was a good choice here. Okay, maybe I can put 0.48. And then I believe that's it. Let's just add one more. Just arbitrarily, I'm going to add a normal curve, normal density to this one. Just let's say I want to compare. Okay, what's the shape of a normal with the same mean and the same standard deviation to the first gamma we add? But now I've updated the name here, so I'm going to call it shape 1 and rate 1. Okay, I add one more curve to this plot. Again, if you wanted to see this on the whole thing, okay, because you don't see the beginning of the normal curve in the first plot, I could have called this x lim c. Let's start it at let's say -2. Okay, and then let's finish it at whatever, 7. Again, this is kind of manual, but let's see what we get. Okay, now I see pretty much everything. Now, just as a comment, this one, the orange one, the first one, you see, I've told it to go up to up bound, but up bound is slightly less than 7. 7 being the argument here. So you see, it's not going to the full range. Of course, you could then change up bound if you wanted to see where it's going. And yeah, I believe that's it. And actually, well, maybe one thing to mention, you see, R is kind of smart here in the sense that when I'm adding a curve to the plot, I haven't specified those arguments, from and to. They don't. R apparently doesn't need it. It's going to plot the curve on the plot on the whole range of the plot that's already there. Okay, so that's maybe a nice feature. Okay, I believe that's it for density function. We can then plot the CDF. Okay, again, I'm going to use curve because the CDF of a continuous random variable is a nice smooth function. Let's try again here. There's going to be mistakes everywhere because I need to update shape to shape 1 and rate to rate 1. The rest should be fine. Okay, CDF of gamma. There you have it. Again, I'm plotting this to up bound. Okay, let me just change it to 5 to see a bit more. Okay, we see a bit more. You see it towards, at the value 8, we're pretty much at the value 1. Just for fun, we're adding the normal, again, update shape to be shape 1, rate 1. Okay, it's quite different. Of course, the normal doesn't have the same CDF as the gamma. And then here, a line will just add the line at 1 here. Okay, a little dotted line. And then, yeah, I think that's all I wanted to show with the CDF. So we've been able to plot the PMF, the CDF of a discrete random variable, then the density and the CDF of a continuous random variable. One last thing. So those are, of course, theoretical functions. Let's simulate a sample. Okay, so I generate random data, and then let's plot the histogram of that data and the empirical CDF of that data. Now, one thing, in case you don't know, when you're generating random things in R, you can to be able to replicate your results, you can set the seed to something, which then will mean once you repeat the same call to generate random things, you're going to get the same thing. Let me just illustrate, because it wasn't clear at all what I said. If I type R norm, okay, you're going to generate me 10 observations from the standard normal. I do it again, you get different ones. Do it again, you get different ones. Do it again, you get different ones. But if I set my seed to any number here, I set it to pi, okay? This in R pi actually gives you the pi. If you do it now, okay, I set my seed and then I generate, okay, I get a set of numbers, it's different than before, but if I call this again, okay, those are the same numbers. Okay, so you can replicate replicate the randomness. Okay, but now let's do what I wanted to do. I'm simulating. So with in R, the syntax is R, then the name of the distribution. Those are the functions you can use to simulate observations from given distributions. I'm going to simulate from R gamma with a shape of 1 and a rate of 1. Sorry, those arguments declared over there, shape 1 and rate 1. Okay, I'm here arbitrarily, let's have a sample of size 10,000. Okay, and I want to see what's the shape of this data. I'm going to plot the histogram. Now here again, there's a few different parameters. X is just my data, my sample. Okay, breaks. Actually, here, maybe it's arbitrary or personal. I like this option breaks equal FD. Okay, usually gives me good results. But let's not have it for now. Let's see. Let's just remove this for now. Okay, I'm using another color, light blue, and again, let's remove proba equals true just to show you the difference. Okay, so I get the histogram. Now this is showing me by default the frequency, like how many observations are from 0 to 1. Okay, there's 2,500 something. Okay, and then from 1 to 2, there's, I don't know, 3,000 something, and so on. If I put back probability equals true, proba equals true, now I see the density. So it's on a density scale. And this is practical because now I could add a theoretical density and see if my histogram, the histogram of my data, fits the theoretical density of whatever. Okay, and then lastly, the last argument I changed here was breaks. It's just that there's different conventions to decide what the size of those bins, what it should be. There's different rules that people have come up with. To me, it seems that FD works better because you see, before FD, the bins were kind of big. Okay, so you don't fully see the shape. While this seems to be a bit better, you see more properly the shape because there's a bit of trial and error. You can also actually explicitly tell R how many of those intervals you want. So if I put a number that's way too high, you see it's not going to be good because it's kind of too granular. Okay, it's actually not too bad, right? But let's say that I had a small sample, okay, 1,000, and then I still had 2,000 breaks there. It's not good because it's kind of too granular. But then if you put breaks equals to FD, usually it seems to be a good rule. Okay, to find a sort of middle ground between how many intervals, but not having enough intervals to see the shape, but not too many that the pattern is kind of too scattered. All right, and then lastly, let's go back to a sample of size 10,000, and I know this is data that comes from a gamma because I generated myself from the computer. So if I add to this plot the curve of the density of a gamma with the right shape and the right rate, it should give me something very close to the histogram. So let's see, drum roll, will it be close? Yes. Okay, it's very on point. So just to explain, the red line is the theoretical density of the gamma with those parameters. The histogram has a bit of random variations because we generate random values, but from this gamma density. Okay, if you generate a huge sample, okay, you should see that the red line will be even closer to your data, to your histogram. You see it's very, very close, and R should be able to handle even 1 million observations, and there it should be very, very close. Yes, very, very close. Okay, and then lastly, let me go back to sample of size 10,000. and let's plot the empirical CDF. Okay, so I think you know what the empirical CDF is. I actually presented this at some point in week 3. Okay, at the very end of week 3. You can review that if you forgot what the empirical CDF is. Okay, but this is from the data. You know, what's the probability to be smaller than 2? Okay, well, in the data you count how many observations are smaller than 2, and you get to whatever value here around 0.6. Okay, and then you plot this for every value, you get the empirical CDF. Again, let's check if it's close to the actually here shape 1 and rate 1. This is the correct. So those functions should be very close. Yeah, you see there. To the naked eye, it's hard to see the difference. If I were to plot instead the shape 2 and rate 2, maybe I change the color here. What's brown? The regular brown. Okay, well, it's quite different because of course it's not the right parameters. You see the data was generated under shape 1 and rate 1. Okay, that's about all I wanted to say in this video. Now in the next videos we're gonna do a few more actuarial things, so simulating under the individual risk model, collective risk models, and things like that. Okay, for now I stop here. Thanks so much for listening.